Hi everyone. I want to give you a warning. Whenever you're doing a trig identity, there's a common error that happens, and that's using circular reasoning. So first, what do I mean when I say circular reasoning? Um, the basic idea here, circular reasoning. Here's a fairly common example of what I'm talking about. Um, my friend never lies. It must be true because he never lies. Okay, so obviously that's an example of circular reasoning because the thing I'm trying to prove, that my friend doesn't lie, the way I'm proving it is by starting with that assumption. Um, and so the way proofs are supposed to go, so a correct proof, whether you're proving an identity or anything else, you start with some statement that's generally accepted to be true. And then you say, okay, well, if this statement is true, then that implies that that this other statement is true, which implies this other statement is true, which implies this other statement is true, right there. And so this is an accepted. It's called a premise in logic. You start off with something that's generally assumed to be true, like for example, sine squared plus cosine squared equals 1. That's a generally accepted fact that everyone accepts to be true, and so you can start with something like that, and then from there you say, okay, the next thing is true, next thing is true, and so forth. But what can happen, especially in trig identities, is you don't mean to do it, but you accidentally, let's say you want to prove that statement D is true, and so you say something like this. You say, all right, well, D is true, therefore A is true, therefore B is true, therefore D is true. And so that's called circular reasoning, because the thing that you're trying to prove, the statement you're trying to prove, is in the argument itself. You're starting off assuming something to be true, which may or may not be true, and then you use that to imply something is true. Here's a good example, a very simple example from basic arithmetic. Prove that -1 equals 1. All right, now of course that's not a true statement, but using circular reasoning, you can prove this is true. Because here's how you do it. You say, okay, -1 equals 1. So therefore, it's generally accepted that if you have an equation, you can square both sides. And so you square both sides, and you have 1 equals 1, and this is true, therefore the original statement must be true. Proven, right? Well, no, because I started off assuming something to be true that actually was the thing that I was trying to prove in the first place. Okay, so let me show you an example in trigonometry where this this danger of using circular reasoning can come in. So let's say you want to prove that sine squared of theta divided by cosine of theta is equal to secant theta minus cosine theta. Okay, so now this is not obvious that this is true. We're trying to prove that this is true. So here's the mistake. I'll write down this is the mistake. I'm going to do it wrong on purpose here, or the wrong way to do it. All right, so you say, oh, it's an equation. I know what to do with equations. You do something to both sides, right? And so you do something like, cosine of theta, cosine theta, and then the cosines cancel. You have sine squared, and then you can distribute. Secant is 1 over cosine, so 1 over cosine times cosine is 1, minus cosine times cosine is cosine squared. Okay, and then you say, oh, look, add cosine to the other side. Cosine squared plus sine squared equals 1. Okay, but that does not prove, although the end is true, but you cannot assume the original statement is true. That's what we're trying to prove. It's exactly like, it's just a more complicated example of saying -1 squared equals 1. Excuse me, -1 equals 1, therefore square both sides. So the fallacy here is this. It's a misuse of that both sides rule. So you can only use that both sides rule, the rule that says if you have an equation, you can do the same thing to both sides of the equation if the original statement is assumed to be true. Okay, so there's where the circular reasoning comes in. I was saying I assume this part in purple, sine squared over cosine equals secant squared minus cosine. I was assuming that to be true. Therefore, I can do something to both sides, etc., etc., etc. So that's the flaw in the logic there. And so here's the correct way to do it. So whenever you're doing a trig identity, you have to avoid. I know it's really tempting because we're so used to, from algebra and so forth, we're so used to doing stuff to both sides of an equation, but we cannot assume it to be true to begin with. And so here's the correct way to prove something is true. So once again, prove that sine squared over cosine squared equals secant squared minus cosine theta. Okay, so you have to start with, like, it has to be sort of like a linear progression, like over here. You have to start with some statement that's generally known to be true. And then from that statement, you say, okay, well, that implies something else, which implies something else, et cetera, until you end up with the statement that they're equal to each other. Okay, so here's what you do is you start with one side only, because we don't know if this is true or not. That's what we're trying to prove. So you can't start with the equation itself. So let's just start with this. In some textbooks, they say LHS for left-hand side. The left-hand side of the equation is this. And then you can say, all right, well, it's generally accepted that sine squared theta plus cosine squared theta equals 1. I'll call that step 1. So that's a generally accepted fact that sine squared plus cosine squared equals 1. Okay, so if that is true, then statement 2, then you can say that sine squared theta equals 1 minus cosine squared theta. That I can do because I'm starting with something that's known to be true. So if something's known to be equal, then you can move things around, do stuff to both sides to your heart's content. All right. So now that I've established that sine squared is equal to 1 minus cosine squared, then my next statement is going to be that sine squared theta divided by cosine theta, which is the thing I'm starting with right there. Well, it's also generally accepted that if two things are accepted to be equal, then you can replace one with the other. So sine squared, I can replace it with 1 minus cosine squared theta over cosine theta. Okay, so now I can take it the next step. I can say that if two things are being added or subtracted, I can divide each of them by the denominator. So I can say that this is the same as 1 over cosine minus cosine squared over theta, cosine squared theta over cosine theta. Okay, and then it's generally understood that 1 over cosine right there is it's equal to secant, because secant by definition is the reciprocal of cosine. And then cosine squared over cosine, a pair of cosines cancel because it's an accepted fact that x squared over x is equal to x, right? Because 2x, subtract your exponents, and so this equals cosine theta, and that is my conclusion. And in some textbooks, they say, and that equals the right-hand side right there. And that's what I was trying to prove, that this left-hand statement is equal to that right-hand statement. And this proves it. I basically, I say, because A is true, then B is true. And if B is true, then C is true. C was this, then D is true, then E is true, like that. So that is the correct way to do a proof of any kind of trig identity.